In this lesson, we're going to define a rational expression in our main unit of rational expressions and equations. But right now, we're just going to look at what is a rational expression, how can we define it, and what can we do to work with it. So when we talk about a rational expression, we're talking about something that can be written in fraction form. Okay? So you might be familiar with rational numbers as things like 2/3 is a rational number, right? Or 7/8 is a rational number, okay? So if they can be written as a fraction, we consider that as a rational number. So what we're going to be dealing with now, though, is not just rational numbers, but rational expressions, which means that they involve variables. So one thing would be like 1/x. This is considered a rational expression, right? Using both variables and numbers, like 1 and x, right? m/m plus 1. This is also considered a rational expression, right? So again, there's variables and constants associated here. Okay, and it can be not just linear, but it can be quadratic, right? So this is a quadratic expression of y squared plus 5 divided by another quadratic expression of y squared plus 7x minus 10, right? Again, it's rational, it can be expressed as a fraction, okay? So the other thing to keep in mind is that a single term is still considered a polynomial, right? Even if it's just 7, okay? Like the number 7 is still considered a polynomial, and it's still considered a fraction, right? It's still considered rational because it can be written as 7/1, okay? And constants are just a single term polynomials called monomials, okay? The other thing that we can consider is that something like 5x plus 8, you can still consider that as a rational expression because, again, you can write it as 5x plus 8 over 1, okay? So it can still be considered rational. So essentially what we're doing is we're creating fractions using rational expressions using variables, right? Linears, quadratics, okay? The thing we need to identify, though, with rational expressions is that fractions are problematic if we ever try to divide by 0, okay? And when there's a variable in the denominator, that can cause division by 0. So if we look at this particular example here, the expression x plus 7 divided by x minus 3. So two linear expressions, right? But there could potentially be a problem. If we have x plus 7 divided by x minus 3, we are not allowed to divide by 0. So if this denominator here of x minus 3 is ever equal to 0, we have a problem. So we always have to look at the denominators of our rational expressions and say, what are my non-permissible values? What are values that my variable can't equal because it would cause division by 0? So what you do is you take your denominator, so in this case x minus 3, and we're going to set it equal to 0. So x minus 3 equals 0. And what value of x would cause that? And you're just solving that equation, adding 3 to both sides. You're saying that if x were to equal 3, then I have a problem with my rational expression. I'm dividing by 0. So anytime you're going to see these rational expressions or rational equations, you're also going to see this list of non-permissible values, values that the variable cannot equal. So you'll see this, this expression followed by x cannot equal, so the equal sign with the line through it, cannot equal 3, right? So x can be anything, you can plug it in, but if it's equal to 3, it's problematic. You're dividing by 0 and you can't do that, okay? So let's take a look at these examples. These are all examples of rational expressions, and our job right now is just to define the non-permissible values, right? What values cannot be used for the variables, okay? So here in example A, we have 5t divided by 4sr squared. So there's actually 3 variables involved here. And we're not trying to solve anything, we're just trying to say what values would cause the variables to be equal to 0, and the denominator to be 0, and then we're problematic. So 0 can be in the numerator, that's fine. 5t can equal 0, and that's okay. Okay? So if 5t is equal to 0, we're just doing 0 divided by something, and no problem. Okay? That's all right. What we want to avoid is the denominator equaling 0. So we don't really even need to evaluate anything with the numerator. We just want to look at where will the denominator be equal to 0. So we look at this denominator, okay, 4sr squared being 0. What would cause that expression to equal 0? And we've got 2 options here. Okay, we're just going to have some technical difficulties here. Just give it a second. We have 4sr squared being 0. What's going to cause those problems? if s were to equal 0, right? If s were to equal 0, therefore this whole expression would equal 0, right? Because you have 4 times 0 times r squared, and it doesn't matter. When you're multiplying by 0, the whole thing would end up being 0, okay? What about if r was equal to 0, right? Again, same thing. If r is going to equal 0, then the entire expression of 4 times whatever s is times 0 squared is just going to equal 0. So my non-permissible values in this particular example are that s cannot equal 0, because it would cause division by 0, and r cannot equal 0. Again, it would cause division by 0. Okay? Let's look at this next example. So we have 3x divided by x times 2x minus 3. Again, this is a rational expression. It's being written as a fraction. And again, what we're looking at is, okay, when is the denominator equal to 0? So I just take my denominator, which is x times 2x minus 3, and we ask ourselves, okay, what values of x would cause that to equal 0? And this is something very familiar that we've seen with quadratics before, where, wait a minute, these are two factors that are multiplying to give me an answer of 0. And if two things are going to multiply to give me 0, then one of them has to equal 0. So either the x has to equal 0, or the 2x minus 3 is going to be 0, right? And then we can just solve each of those. Well, x minus 0, x equaling 0 is on its own, so that's one of our non-permissible values. And then here we just solve this linear equation such that 2x is equal to positive 3 and x is equal to 3 over 2. So again, my non-permissible values, my values that would cause me to divide by 0 would be if x was equal to 0, so we say x cannot equal 0, and x cannot equal 3 over 2. Because if I were to substitute 3 over 2 in for x, the denominator from this factor here would end up being 0, would cause the entire denominator to be 0, and that leaves us with issues. Okay, let's do one final example here. So if we have the fraction, again, rational expression, 2p minus 1 over p squared minus p minus 12. So again, we're looking at that denominator. What would cause the denominator to equal 0? Right? Well, again, this is a quadratic. How do we solve it when it equals to 0? Well, we need to factor it. Okay? So we will factor this, and p squared minus p minus 12 factors into p minus 4 times p plus 3 equal to 0. We again see that these are two things multiplying together to be 0, so one of them must be 0. So either p minus 4 is 0, leading us to p being 4, or p plus 3 being 0, leaving us with p equal to negative 3. So again, these are our non-permissible values. If I were to plug p equaling 4 up in that original equation, right, I would end up trying to divide by 0. Or if I plugged in p as negative 3 into that original equation, again, I would be left with trying to divide by 0. And let's just confirm that with this one example here. Okay, so let's take that value of 4, and we can say, okay, I'm going to plug in 4 everywhere where there's a p. So 2 times 4 minus 1, all divided by 4 squared minus 4 minus 12. If we simplify that, 2 times 4 is 8, 8 minus 1 is 7. No problem. But if we simplify the denominator, 4 squared is 16, 16 minus 4 is 12, and 12 minus 12 is 0. This is now an expression that's fraction is being divided by 0, which is a problem. You cannot do this, so that is why we say that the non-permissible value is that p cannot equal 4, and the same thing would have happened with negative 3. Okay? Now, similar with equivalent fractions, right, we can also create equivalent rational expressions by, again, multiplying by this clever form of 1. So let's just briefly pause and think about what we know with fractions, right? So if I were to have, let's say, the fraction 2/3, okay? If I want to make equivalent fraction to 2/3, you might easily say, oh, 4/6, right? But what you've essentially done here is you've taken 2/3 and you've multiplied it by 2 over 2. You've essentially just multiplied it by a form of 1, right? Because 2 divided by 2 is just 1. And this allows us now to rewrite the same value. It still has the same inherent value, because when you multiply something by 1, nothing actually changes. Okay? So that's kind of how we would have created those equivalent fractions, right? And the same thing can be done with these rational expressions, right? So we can start looking at this expression such that 7s divided by s minus 2 with the inequality that s cannot, the non-permissible value with s cannot equal 2. Okay? So what we've got here is this rational expression that has our non-permissible value at 2, because that would cause division by 0. if we wanted to, for some reason, write an equivalent expression, right? So we're going to take this 7s, and it's over s minus 2. Whatever the case may be, we are trying to write an equivalent fraction. We just multiply whatever we want. Let's say we multiply it by this clever form of 1 of s over s. It doesn't change the inherent value because you're multiplying by 1. So remembering multiplying fractions, we just multiply the numerators together, so that would become 7s squared divided by, we'll just leave it in factored form, s minus 2 times s. But be careful when you do this, because what we've done now is that we've added a new non-permissible value. When we started up here, the only non-permissible value was 2, right? S couldn't equal 2. But now we've added a factor in our denominator, which has now added a second non-permissible value, right? So now we have to clarify that, look, s can also not equal 0 if we're going to write it in this way, okay? So we've added, every time you create a new expression, it could potentially lead to more non-permissible values. So every time you do this, add to your list of non-permissible values, okay? In simplifying rational expressions, okay, again, what we're going to do here is we're trying to look for those common factors, right? So just like we can expand them, make them bigger by multiplying by clever forms of 1, we can also see if there's any common factors. So for instance, let's look at a simple example of 9 over 12, okay? Both of these numbers are divisible by 3, so if you were to divide both by 3, what you then see here is 3/4, okay? But I want to show you a slightly different way of looking at that. Take 9 over 12. And yes, you realize that it's divisible by 3, but actually show how you factor the 3 out. Rewrite 9 with 3 as a factor. It's 3 times 3. Okay, we've rewritten 9 as 3 times 3. And because we know 3 is the common factor, we're also going to rewrite 12 using a factor of 3. 12 can be rewritten as 3 times 4. Then what you can do, because these are being multiplied, okay, because they're being multiplied, these can cancel, right? Because essentially what you have is, you can also rewrite it like this, where it's 3 over 3 times 3 over 4, right? And this is essentially just 1, so it doesn't really need to be there, and we get that answer of 3/4. Okay, obviously that's a longer way to do it with constants, but it's that understanding of why that works that's going to help us with expressions that involve variables, right? So we consider trying to simplify this m cubed t divided by m squared t to the power 4. Again, remember what those exponents tell you. If we have m cubed, that's the same as m times m times m, and then times t. And our denominator here of m squared t to the power 4, that's like m times m, and then times 4 t's. Okay? What you can then look for is, as long as there's a common factor in both the numerator and denominator, you can cancel that out, because it will essentially be this form of 1. Because this idea of m over m, that's just 1. So they can kind of be canceled. We're reducing here. Okay? And then we have another pair, right? We have another m over m, so those can be canceled as well. A t over t would cause a clever form of 1, right? So this t can cancel with this one. Nothing else can cancel, so we are left with, on the numerator, a single m, and in our denominator, t cubed. Okay? Again, that's probably a longer way of looking at it, when you could go back to look at that same expression, m cubed t divided by m squared t to the power 4, and look at each of the variables individually. Look at the m's and look at the t's. So I've got m cubed in the numerator and m squared in the denominator. What's the lowest one that they have in common, right? They both have at least m squared, so I can factor out an m squared from both the numerator and the denominator. Right? I also look at, okay, well, what's in common with the t's? Well, they both have at least one t, so a t is a common factor in both. Right? So that's kind of like our GCF. And then what's left in that numerator? Well, I've got m squared here. I need one more m, right? And I've already got the t taken care of. Okay? And then again in the bottom, I've already got the m squared. I only have a single t, but I need t to the power 4, so I need t cubed here. Right? I have identical factors in the forms of m squared t over m squared t. These can cancel, and I'm left with m over t cubed, much like I was when I expanded the whole thing out. Okay? So again, you're just trying to look for these common factors that you can simplify as best as possible. Okay? Keep in mind, things change a little bit differently, right, when you are now adding. All right, so if we've got m squared t plus t squared over mt squared, again, you're looking for that greatest common factor in both your numerator and your denominator. So here in the numerator, the only thing that's in common between those two terms is just a t, right? The t can factor out, and then I can write that as m squared plus t, right? Because if I were to expand this out, t times n squared would give me my m squared t, and t times t would give me my t squared. And then I can rearrange that denominator as t times m squared. So the common factor, right, notice how everything's been written in factored form here, and the t's are common factors and are canceled out, and our simplified version is m squared plus t divided by m squared. You cannot cancel this m squared with this m squared. You cannot do that because it is not a common factor of both numerator and denominator. Because of this plus sign, because there are two terms in this numerator, and m squared is not a common factor, you cannot cancel those values. This is your final answer. Okay? This is kind of very similar to what happens when you're simplifying with radicals and when you're doing the quadratic formula and trying to get exact roots, right? You're looking at this, 6 plus or minus 3 root 5 all over 3. Look at your numerator. Is there a common factor? Yes. It's both divisible by 3. So we factor out the 3 and we rewrite it as 2 plus or minus root 5, right? Because again, if you did 3 times 2, you'd get 6. If you did 3 times root 5, you'd get 3 root 5. And you can rewrite the number 3 as 3 times 1. And then once again, these are in factored form. The 3's can cancel, right? Because that's just 3 divided by 3, which is 1. And you're left with 2 plus or minus root 5 over 1. But division by 1 is just itself. So you could just omit that and write it as 2 plus or minus root 5. Okay? So again, simplifying these rational expressions. Okay, so the idea behind simplifying them, and I can't stress this enough, is factor, 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 factor. Whenever you start to simplify something, start by looking at the expression and saying, can I factor this? How can I factor this? Is there a greatest common factor? Is this a quadratic that can be factored? Do I need to use decomposition? Any of those things. So I start by looking at this. I say, okay, 3x minus 6, how can I factor that? Well, there's a 3 that can be factored out of that, so it's 3 times x minus 2. Then I look at the denominator and I ask myself again, can I factor this? Well, my a value is not 1, it's 2, so I'd have to use decomposition, which is fine, and we run through that process. So I would start by multiplying my a and my c value together. 2 times negative 10, that's negative 20. Okay, and then I'm looking for numbers. What two numbers multiply to give me negative 20, but add to give me positive 1? And they are 5 and negative 4. Right, and that's how I decompose my middle term. So it's now 2x squared plus 5x minus 4x minus 10. And I factor by grouping, leaving my numerator as it is for now. Right, and that then becomes, in these first two terms, the only thing in common is an x, and I'm left with 2x plus 5. And in these next two terms, I can factor out a negative 2, and I'm once again left with 2x plus 5, so that my denominator factors into x minus 2 and 2x plus 5. Only after you've factored your expression can you look at canceling. Is there a common factor in both the numerator and the denominator? In this case, yes, the x minus 2. The x minus 2 is a common factor in both numerator and denominator. So the x minus 2's can be canceled. But before we fully cancel them, we also would like to state what our non-permissible values are. So again, looking at our denominator, what values would cause this denominator to equal 0? Well, if x was 2, this factor would be 0, and then the whole thing would be 0. So I list up here in my non-permissible values, x cannot equal 2. The other thing x cannot equal would come from when the other factor in the denominator would be equal to 0. So if this 2x plus 5 was equal to 0, that would be a non-permissible value. And if we rearrange that and we subtract 5 and divide by 2, our other non-permissible value would be when x is negative 5 over 2. Okay, so x cannot either equal either of these things, or else it's going to cause division by 0. Now when we go back to simplify, we've said that x minus 2 is a common factor, leaving us with our final answer here, where it's 3 divided by 2x plus 5. And this is as simplified as we can get at this point. Okay? Same thing here in b. All right, so our expression is a linear over quadratic, right? 1 minus t divided by t squared minus 1. Factor, factor, factor. So in our numerator, it doesn't appear as though anything can be factored out, so we can just leave it as 1 minus t. Our denominator, you should be reminded of difference of squares, right? It's two terms, both perfect squares, separated by a minus sign, so it will factor into t plus 1 and t minus 1, okay? Once our denominator is factored, that allows us to state our non-permissible values. What would cause these factors to equal 0? Well, t plus 1 would be 0 if t were to equal negative 1, so that's one of our non-permissible values, and t minus 1 would equal 0 if t was equal to 1, so 1 is also listed as a non-permissible value. Now we're trying to see, is there a common factor in both numerator and denominator? And it looks like there is, but it's just not quite right, because this is a positive 1 and a negative t. This factor here is a positive t and a positive 1, so it's not quite matching up, right? This is again a positive 1 and a negative t. This is a negative 1 and a positive t. But one thing you can be on the lookout for is being able to just factor out a negative 1 from anything. So if we just factored out a negative 1 from the numerator and rewrote that as negative 1 plus t, now what we have, if we just rearrange it, is negative 1 times t, right, a positive t, minus 1. And by factoring out that negative 1, we were able to switch our signs just right, and now t minus 1 is a common factor of both the numerator and the denominator, so it can cancel, leaving us with a final simplified expression of negative 1 over t plus 1. And that's our simplified expression with, of course, our non-permissible values being stated at negative 1 and 1. We don't now go back and erase the negative 1 just because we've canceled out that t minus 1 term. The non-permissible values come from the original expression, not the simplified expression. Okay. So other times you might not be able to get an exact value of what the variable can and cannot equal, but you know that there's a particular relationship between those variables that must be met. Right? So for instance, maybe you can't say that, oh, well, x can't equal 2, but you know that whatever the value of x is, it can't equal y, because that would cause a problem. Right? So let's, again, take a look at this. So if we were to look at this expression, 16x squared minus 9y squared divided by 8x minus 6y, again, my suggestion when trying to simplify this is to factor, factor, factor. Right? So the first thing I'm going to do here is look at that numerator, 16x squared minus 9y squared. Again, that should be screaming at us. Difference of squares, right? They're both perfect squares separated by a minus sign. So that's going to factor in that special way where it's going to be 4x plus 3y, right? The square root of each of those terms, and then 4x minus 3y. Right? And in our denominator, what's our common factor between 8x and negative 6y? And the best we can get is a 2, right? But we can still factor out that 2, and then we're left with 4x minus 3y, okay? Now, in stating our non-permissible values, right, we can't ever say it's going to equal 0, but there might be a relationship between x and y that just won't work. So again, our non-permissible values are going to come from our denominator, so 2 can obviously never equal 0, but 4x could equal, right, 4x minus 3y could equal 0 if the particular arrangement, right, and the relationship between x and y were valid. Right, so what you want is an expression, note it doesn't just say value, but an expression that represents the non-permissible values. So again, you would just isolate x here. So you'd add 3y, 4x is equal to 3y, divide both sides by 4, x is equal to 3y over 4. Right? So any relationship where the value of x is exactly 3/4 the value of y, that's going to cause division by 0 in this particular expression. Okay? Again, simplifying this, okay, so this was the factoring of the denominator allowed us to find that non-permissible expression relationship. Going back to how we have this factors of 4x plus 3y times 4x minus 3y in the numerator and 2 times 4x minus 3y in the denominator, we should see this common factor of 4x minus 3y. That again can be canceled, leaving us with a simplified expression of just 4x plus 3y divided by 2. Okay? What we've been asked to do in part C here is evaluate the expression for x equals 2.6 and y equals 1.2, and to show two ways to determine that answer. The first thing we're going to do with that, though, is make sure that those values don't cause us problems with our restrictions, right? So remembering back from the previous slide, our non-permissible restriction values were x equaling 3y over 4. Okay, so x equaling 3y over 4. We've been given values of x and y such that x is 2.6 and y is 1.2. And we're just trying to make sure that this doesn't happen because it would cause division by 0. So if we were to plug 2.6 in for x, okay, and we were to plug in 1.2 in for y, would these equations equal each other? Okay, and quickly evaluating that, 3 times 1.2 divided by 4, we get 0.9. And 2.6 does not equal 2.9, so this combination will work. Okay, we don't have a problem here. So now we can actually go about and evaluate our expression. Okay, and again, it's asked us to do it two ways, and the two ways we can do it are by plugging the values into the original expression, which was our 16x squared minus 9y squared, all over 8x minus 6y. Right, where we could take our values of x being 2.6 and plug it in for x. And take the value of 1.2 and plug it in for y. Right, and then just evaluate. Okay, so the numerator then becomes 16 times 2.6 squared minus 9 times 1.2 squared. And our numerator becomes 95.2, and we evaluate the denominator, 8 times 2.6 minus 6 times 1.2. That denominator becomes 13.6. Do that final division, 95.2 divided by 13.6, we get a value of 7. Okay, evaluating the expression at those two values gives us a value of 7. The second way we can evaluate this is by using our simplified expression that we completed over here. This 4x plus 3y divided by 2. Right? So if we just went to the 4x plus 3y divided by 2, and then we used our value of x is equal to 2.6 and y is equal to 1.2, right? And then we evaluated this, it's just a matter of, well, 4 times 2.6 plus 3 times 1.2, that's 14, and then 14 divided by 2 is 7, okay? So this is to demonstrate the benefit of simplifying a rational expression. If we simplify it first, it makes any subsequent calculations go a little bit faster, right? Because we're not having to plug them in as many spots, okay? Because we've simplified it as much as possible, and it can make those calculations easier, right? So that's that lesson on just rational expressions, how we can simplify them, how we can factor them, how we can find non-permissible values, and these would be practice questions from your textbook that you would want to complete to ensure that you understood and can do these types of problems.